welcome to the session, and we will continue with electrostatics. In the previous two sessions, we learnt about how objects acquire charge, and in order to charge an object, what are the methods that we can employ. So the previous two sessions dealt with qualitative aspect of the chapter, the electrostatics chapter. Today we are going to delve into the quantitative aspect. That means we are going to talk about numbers today. Okay, so welcome to the session. Pooja, Anuj, welcome, and Rajesh, good evening. So guys, let's see what we are going to learn today. So we know that if there is a positively charged particle, so if there is a positively charged particle of charge q, okay, and there is, let's say, another positively charged particle of charge q2, and if they are separated by some distance, let's call this distance as r, okay, then we know that these particles will repel each other. Okay, what we don't know yet is that how much force will they exert on each other. That is something that we don't know. Okay, now this force, okay, like experiments have revealed that this force is proportional to the product of the charges. Okay, so if we increase these charges, the force will increase. Okay, and experiments have also shown that this force is inversely proportional to the square of distance between the particles. Okay, when we combine these two results, we discover that force is some constant into K1 into K2 by R square. So this is how we write the force that these particles will exert on each other. Okay, here K is a constant that depends on medium. It is a constant, okay, that depends on medium. For different medium, okay, K would be different. Now, what do I mean when I say medium? It basically means that the surrounding in which these particles are kept. For example, these particles could be kept in vacuum, okay, or they might be kept, let's say, submerged in an ocean. So what I'm trying to say is that there may be water, surrounding these particles, and it extends up to large distances on all sides. So whatever I'm writing, I'm assuming that the medium in which the particles are kept, that medium extends up to infinity. It extends up to large distances on all sides. Because if it doesn't extend up to large distances on all sides, then the things that we are studying, they are not strictly valid. Like, we have to then change the expressions a bit. Okay, so right now we will assume that whatever the medium it is, whether it's vacuum, whether it is air, whether it is water or any other liquid, any other medium, that extends up to infinity on all directions. And so K will change when we change the medium. Okay, K is also written as 1 by 4 pi epsilon. Okay, now 4 pi is the same constant that, like, it's a constant value which you are well aware of. 4 is the numeral 4 and pi is that good old pi that you see when you study about area of a circle or the circumference of the same pi. What exactly is epsilon? Okay, so we pronounce it as epsilon. This is how we pronounce it. This is epsilon. This is the symbol. Okay, for example, we call this symbol as alpha, we call this symbol as beta. So this symbol is called as epsilon. Okay, and it represents a physical quantity. It represents a physical quantity which we call as permittivity. Okay, we call as permittivity. Okay, we call as permittivity. So what exactly is permittivity? Permittivity is a number, you can say it's a number associated with a medium which indicates the responsiveness of the medium towards charges. Okay, the higher this number is, the more responsive the medium is. The medium will react to the presence of charges to a greater extent if this number is greater. Okay, so epsilon represents permittivity. For vacuum, okay, for vacuum permittivity is represented by the symbol epsilon with a 0 in the subscript. Okay, it is pronounced as epsilon naught. Okay, this is how you will hear people calling it out, pronouncing it. It is called epsilon naught. Okay, it indicates permittivity of vacuum. It is also known as permittivity of free space. Okay, and the value of 1 by 4 pi epsilon naught is 9 into 10 raised to power 9 Newton meter square per coulomb square. It is better if you remember this value, everyone. Okay, because you would be using this in a lot of questions. Okay, here let me also tell you that if nothing is mentioned about the medium, then you have to consider that the particles are either kept in vacuum or they are kept in air. Okay, for air also the value of permittivity is very close to the value of permittivity for vacuum. Okay, it is slightly greater, but the difference is not appreciable to be considered in the calculations. So we don't consider that difference in calculation. So for air we consider the permittivity to be same as the permittivity of vacuum. For any other medium, okay, the permittivity, okay, permittivity of any other medium will be greater than the permittivity of vacuum. Okay, if you want to include vacuum also in the list of mediums that you are considering on the left hand side, then you can put an equality also, which also means that this ratio, okay, this ratio will always be greater than 1, and this ratio has got two names. It is called the relative permittivity also. And there is another name given to this. It is called dielectric constant also. And when we call it as a dielectric constant, we represent it with a capital K. Okay, so this is called dielectric constant also. Okay. Okay, and from here we can remember this, that dielectric constant for any medium, okay, any medium other than vacuum is greater than 1. For vacuum it will be equal to 1. Even for air it will be greater than 1, although the difference won't be too large. Okay. Alright, so I hope we are clear till this point. Okay, I'll summarize what I have told you till now. Okay, I'll summary till now in today's session. So I have told you that if there are two particles with charges q1 and q2 and they are separated by distance r, then they will exert force on each other. The direction of force will depend upon the polarity. I'm assuming that these charges have the same polarity, and we will write this force as 1 by 4 pi epsilon naught q1 q2 by r square. Okay, this epsilon naught is called the permittivity of the medium. If the medium changes, permittivity will also change. For any medium other than vacuum, permittivity will be greater than the permittivity of the vacuum. Okay, for vacuum, this entire number becomes 9 into 10 raised to power 9 Newton meter square per coulomb square. Alright, so this is what I have summarized till now. Now with that, let's attempt some questions. Let me give you some very simple questions, and we'll start from simple ones. We'll move toward more complicated ones. Okay, so let's start with a very simple example. So I have one charge particle. Let's say the charge on this is 2 nanocoulomb. Okay, and then I have another charge particle on the charge on which is, let's say, 1 millicoulomb, and let's say these charges are separated by 2 centimeter. Okay, and let's say both the charges are positive, so they will repel each other, and I want you guys to calculate that what will be the force that they will exert on each other. So can you give it a try, guys? Okay, it's a very simple question. I've just given you a formula. You have to punch in the numbers in the formula and you have to get the right answer. Okay, very simple formula. Okay, so Aditya, Anuj, Pankaj, Brajesh, do you want to give it a try? What would be the force here? I'll start calculating. Okay, by that time I hope that by the time I solve this question and I turn towards the screen, I do see some responses from you guys. So force will be written as 1 upon 4 pi epsilon naught, we know the value of this, into q1 into q2 divided by r square. So it will become 9 into 10 raised to power 9. Okay, that's the value of k, into q1 q2. So that will become 2 into 10 raised to power, that's because nanocoulomb is given. Okay, and then 1 millicoulomb, that's 10 raised to power minus 3 coulombs. Okay, divided by r square. R is given in centimeter, I will convert it into meter. So it will become 2 into 10 raised to power minus 2 square. Okay, now I have to finish the calculation, so let's do that. So this 10 raised to power 9 and 10 raised to power minus 9 gets cancelled. Here we will get 10 raised to power minus 4, this is 10 raised to power minus 3. So when we cancel this out, we're left with a numerator, with a 10 in the numerator. Okay, so eventually we would be left with 9 into 2, okay, into 110, that was left because of these two, and then divided by 4. So it ultimately becomes, this will become 5. So 45 Newton is the right answer to this question. Has anyone given that answer? Not yet. All right, everyone. So that would be the answer here. Okay, so simple question, I would say, nothing much complicated here. You just had to punch in the value and you would have got the answer. Now let me increase the complexity a little bit. Okay, so this time what is happening? This time, let's say you have 4 particles, or should I go with 3 first? Let's go with 3 first. Okay, so let's say 3 particles are kept on the vertices of an equilateral triangle. So this is an equilateral triangle of side length, let's say 2 centimeter. Okay, and at all vertices there are charges. So there is a 2 nanocoulomb charge here, there is a 2 nanocoulomb charge here, and there is a 1 millicoulomb charge here. Let's name these charges as A, B and C. So the charges are kept like this. We want to know the net electric force on B. Net electric force on B. Okay, so how many of you can solve this question? Hi Arsh, welcome to the session. Do you think you can solve this question? It's an equilateral triangle. The side length is given to be 2 centimeter. There are 3 particles kept, A, B, C. A is 2 nanocoulomb, B is 1 millicoulomb, C is again 2 nanocoulomb, and we want net electric force on B. Can you solve this question, everyone? So in this question, why we are talking about the word net? Okay, because I can clearly see that apart from B, there are 2 particles, and both these particles will exert a force on B. Okay, so this particle A will exert a force on B. Okay, let's call this as F, and again C will also exert the same amount of force because everything is same. The distance here is same, the product of charge of these 2 particles is same. So this would be the force, and the angle between them would be 60 degree. Okay, so to find out the net force, I will invoke the formula for resultant of 2 vectors. The formula says, like, if you are trying to find out resultant of 2 vectors, the formula is a square plus b square plus 2ab cos theta. Okay, so here it will become f square, okay, plus f square plus 2ff into cos 60. So cos 60 and 2 will become 1. So we ultimately have 3f square, or in other words, we have root 3f. And if you notice that the force between a 1 millicoulomb charge and a 2 nanocoulomb charge separated by a distance of 2 centimeter, we calculated the same thing here. Okay, we calculated the same thing as 45 Newton. So I can now directly substitute this formula value. So it will become 45 root 3 Newton. So that would be the net force acting on particle B. Okay, so that net electric force acting on particle B. So are we good with this, everyone? Are we good with this example? Because if we are good with this example, let me increase the complexity level a bit more. Okay, so this time, instead of having a triangle, let's say we are talking about a square. Okay, so this time I have a square of 2 centimeter, and then I am placing particles on this. Okay, so I am placing a particle here. Let me use symbol instead of number this time, or in that case, let me also replace this 2 by a symbol. Okay, so let's say the side length is A, okay, and this is a square, okay, and then I have another charge Q here, okay, and then I have a charge capital Q here, I have a charge capital Q here, okay. Now what I want is that we call these particles as A, B, C and D, and I want net electric force, okay, the net electric force on C to be 0, the net electric force on C to be 0. Now give a thought to this situation, guys. I want the net electric force on C to be 0. Okay, these two particles have same charge, same magnitude, same polarity. These two also have same charge and same polarity. To achieve a net 0 force on C, can all these particles have the same polarity? Can all these particles have the same sign? Yes or no? Can all these particles have the same sign? Like, can all of them be the positive charges? Can all of them become the positive charges? Okay. Om Kumar, Prayas series was the something that we were doing previous year. Okay, so the lectures are still visible. They are present on the YouTube channel. If you want to go over the same sessions, you can do that. All right, this year we are doing the basics to advanced series and the Akar series, of course. If you want to learn mechanics portion or grade 11 portion, you can join the Akar series. You can watch lectures in the Akar series. Anand sir himself is taking the session, so what better can you find than that? Okay, now coming back to this question, are we expecting the polarity to be same if we want net 0 force on C? I'm pretty sure that you are not expecting that, because if all of them are positive, then all these three forces will repel it, and we cannot get 0 force on this. So this and this, A and C, they are given to be of same charge. So let's say if these two are positive, let's say if these two are positive, okay, if these two are positive, then these two must be negative. These two are bound to be negative. Okay, the magnitude of charges is Q. Okay, now what will happen is that which color should use this one? So this D charge, it's an opposite polarity charge, so it will attract with some force. This will also attract with some force, and A being of the same polarity, it will repel with some force, which we should not write as F. Let's call it as F prime. Okay, this force is F. This force will also be represented by same F, because again, same charges, same distance. So these two are going to be equal in magnitude, and therefore I have represented them with the same symbol F. Okay, and this A will repel this Q charge with this C charge along the diagonal. I am writing it as F prime. So to get a 0 force on C, F prime should balance the resultant of these two, and the resultant of these two will be in this direction. It will be equal to √2 times of F. So we will eliminate these two. These two will become √2F. F prime should become equal to √2F, and that will give us the answer. Okay, so question was, what is the relation between these two charges? Okay, the small q and capital Q. So F prime we will write. How will we write? It would be K Q Q. F prime is the force between these two charges. So K Q Q divided by the distance between them is √2A. Remember, it's the diagonal. Okay, diagonal is the distance. So square of that. Okay, I hope this is visible. This will be equal to √2 time of K small q capital Q divided by A square. And now many things will get cancelled. Let's cancel them out. Whatever is getting cancelled, K gets cancelled. Okay, 1 Q gets cancelled here. A square gets cancelled here. So we are left with small q upon 2. √2 square will become 2 is equals to √2 into capital Q. Okay, so from here we get the ratio of small q by capital Q. So this ratio is 2√2. Okay, so we have to maintain this ratio to get net 0 force on C, and we have already discussed the polarity also. Okay, so that is one thing. Now how about we further increase the complexity a little bit? Okay, that was quite complex, right? What am I thinking of 5 particles now? Well, maybe. Okay, so but to do that, let me first talk about the vector form of Coulomb's law. Okay, so Okay, so the formula that we wrote, that is called the Coulomb's law. Now we are going to write it in vector form. Okay, so let's see. So suppose there is a charge particle q1 and there is another charge particle q2. Okay, and let's say this is r1 vector, this is r2 vector. Okay, so we have been given the charges, we have been given their position vectors, and we have to find the force that one particle exerts on the another particle. So let's call this force, let's represent this force as, suppose F21. So F21 would mean force on 2 by 1. We are choosing, this is our choice, we are choosing to represent force on 2 by 1 as F21. So basically whatever number I am writing first, I am writing the force on that particle, force on 2, and whatever number I am writing the second, after the first one, in the second position, that particle would be exerting the force. Okay, so force on 2 by 1. Okay, F21 is force on 2. Now if I have to draw this force, assuming that both the particles are positive, let's assume that. It is not necessary that both are positive, but let's assume that both are positive. So in that case, F21 would be drawn like this. It is the force on the second particle due to the first particle, and we want to write this force using the charges and the position vector. Okay, let's see how we can do that. So for that, notice that if I draw a vector from first particle towards the second particle, this is R21 vector. What is R21 now? So R21, okay, this is position vector of 2 with respect to 1, and it is written as R2 vector minus R1 vector, and the magnitude of this vector will become the distance between the charges. Okay, it will become the distance between the charges. Okay, Aditya, all right, I'll try to go slow. Okay, see, the reason I was going a bit faster was that because my speed is in your control. With lecture being present on YouTube, the speed is totally under your control. Okay, and as we know that these days students and everyone want to consume the content faster. Even if the content is going slow, they increase the speed and see that. Okay, so I think I was getting affected by that, maybe. Okay, English, no Anuj, this B2A series is expected to run exclusively in English, so I'll have to stick to English, although I want to speak in Hindi as well, because yeah, of course I'm very much comfortable there expressing my ideas, but because this series is meant to be taken completely in English, I am trying to stick to that. Okay, so coming back, what is happening here? There are two charged particles, the position vector is given to us. We want to write force on one particle by the other using vector notations. Okay, so we have decided, first we have figured out that this is what would be the meaning of this symbol. We have narrated that. Okay, and we have noticed that the distance between the two particles would be the magnitude of the vector r2 minus r1. So if I have to write the magnitude of the force like F21, okay, this magnitude would be K Q1 Q2 by R21 vector magnitude square. Notice this. Are we good with this? Are we good with this? Aditya, electrostats will start in Akar batch after grade 11 topics are done. Okay, and therefore, in this series we are starting with grade 12 topics, so that any student who is comfortable with Hindi as well as English can actually take benefit of both the series. Okay, now coming back to this question. So this is my equation number 1. Okay, let's say this is my equation number 1. Okay, this is my equation number 1. My next equation is F21 cap. Do you know what cap means? This is unit vector parallel to F21. Okay, so if I go back, F21 means unit vector in this direction. Okay, now tell me guys, is this same as R21 cap? That would be my second equation. Okay, F21 cap, unit vector along the force, okay, is same as unit vector along R21, because if these two equations are valid, then see, to write any vector, we can take the magnitude of that vector and we can multiply that magnitude with unit vector parallel to itself. Okay, this is true for any vector, which means that if I'm trying to write F21 vector, I can do this. I can write the magnitude of this vector and the unit vector along it. So F21 is KQ1 Q2 by R21 square into R21 cap. Okay, and F21 vector will be equal to KQ1 Q2 by R21 square into this unit vector can also be written as the vector divided by its own magnitude, which ultimately leads to the final formula, which is this R21 divided by mod of R21 cube. From where does the cube appear? Square is here, one more here is here. Okay, so F21 vector. So this becomes your vector form. Okay, this becomes your vector form. Now guys, in case, just in case, if you found all these things difficult, what is your option? Your first option is to watch the video at a slower pace, you know, intermittently pausing the video to understand what I said, imbibing whatever I've said, trying to understand what I've said, trying to draw the figure yourself and then matching with what I did here. That is one thing. In case if that also doesn't help you, please feel free to ignore this portion. You will better understand this portion when you become better at vectors. Right now also we are using vectors, but we are not using it to their full potential. We are not using vectors to the full extent while we are solving problems in physics. Okay, you will become better at it as you study more and more topics. So for now you can forget it. You can just note it down in your notes copy, and later on in your subsequent revision rounds, when you go over through this theory, you will be able to understand everything. Okay, now why did we do all this? Like our life was going so great with questions like this. We were able to do everything. Why did we need the vector form of Coulomb's law? Okay, just to do something fancy? No, it's not like that, guys. It will help us. I'll tell you in what kind of situation it can help us. So let me give you an example on that. Okay, so I'm pretty sure that you all know what a pyramid shape looks like. Okay, now this is certainly not a pyramid, but yeah, this can be the base of a pyramid. So if I mark a dot here and then if I connect this dot with all the four vertices, does that look like a pyramid? Yeah, it does. Okay, I was afraid that I almost made these 3 points collinear. I always tend to do that when I try to make a pyramid. Maybe a little bit higher would have been a better figure. Okay, yeah, let's make a better figure. So I guess much better. Anyways, now you have a particle here. So I said that how about if we increase the number of particles from 4 to 5? Let's say, have we done that? Oh, we are going backwards. Okay. Yeah, so Q, capital Q, small q. I want to know the net electric force on Q. I am only interested in knowing the magnitude. Okay. So we have 5 particles now. I did not give you the distances. Let me do that also. So the diagonals are of length 2L, okay, and the height of the pyramid H, okay, this H is actually root 3L, okay. So the diagonals are of length 2L, the height of the pyramid is H, okay. First of all, guys, do you think that the complexity has increased to a great extent now? Because the forces that these particles will exert on this particle, those forces are non-coplanar forces. They don't belong to the same plane, unlike all the previous examples that we did. Okay, in all the previous examples, the force was coplanar, all the forces were coplanar, so it was very easy for us to find out the resultant of those forces. Now the forces are non-collinear. Now, one of the ways is to have a real good 3D visualization of the situation and solve, which probably some of you can do it. For example, if I ask you that what will be the direction of net force on capital Q, most likely you will be able to tell me the net force, the direction of the net force by your intuition, not by the logic. Probably you will not be able to process the logic that quickly, but I'm pretty sure that intuitively you already know that the net force on this Q will be upward, okay, and you know that because you know that by symmetry, the situation is symmetric. Intuitively you can judge that it should be, and there is correct answer. You know, there is obviously there is logic to it, we can talk about that logic, okay, but intuitively also many students, they are able to judge, I'm pretty sure, okay. The question is, how do we find that net force? Okay, now to do this question, whenever you see a situation in which the forces are non-coplanar, okay, whenever you see a situation where the forces are non-coplanar, what you can do is go with the vector form. I'll tell you how, okay. So keep watching. The question has not given us any coordinate system, but that doesn't mean that we can't choose our own coordinate system. So here I see the two diagonals, the diagonals of a square, they are perpendicular to each other. So I will choose this point as the origin, I will choose this point as the origin, and one of the diagonals as x-axis and the other diagonals as y-axis, so that this direction becomes the z-axis. See, this is how I have chosen the coordinate system. How does it help me? Let me name the particle. So let's call this as A, let's call this as B, let's call this as C, let's call this as D, and let's call this as E. So our aim is to find force on E. Okay, now notice that I can write coordinates of all 5 particles. So particle A lies on the x-axis, its coordinate would be L, 0, 0, because this distance will be equal to L. Similarly, particle B will lie on 0, L, 0. Particle C will lie on 0, minus L, 0, and particle D will lie on 0, 0, minus L. Okay, now what about E? So for E particle, it lies on z-axis, so the x coordinate will be 0, the y coordinate will be 0, and the z coordinate will be equal to root 3L. Okay, so we have written the coordinates of all 5 points. Why have we done that? We have done that because we want to write force on E due to A. Similarly, we want to write force on E due to let's say B, and so on. We want to write force on E due to D. Only one was left, maybe we would have written that also. So force on E due to C. We want to write all these 4 vectors. To write this vector, I need REA vector, and to get REA vector, I need RE minus RA. And to write RE minus RA, I need coordinates of E as well as coordinates of A. Okay, so that is my requirement. So if I want to write, let's write these vectors. So RE vector minus RA vector would be coordinate of E minus coordinate of A. So 0, 0. Okay, so minus L I cap plus root 3L K cap. Check this. 0 minus L is minus L, 0 minus 0 is 0, this minus 0 is root 3L. So yes, okay. Similarly REB vector, now I am writing directly. I am leaving it up to you guys to finish this exercise by looking at the coordinates. REB would be this minus this, so it will become minus LJ cap plus root 3L K cap. Okay, REC vector, okay, that will become LJ cap. For C, I wrote the coordinate incorrectly, guys. For C, it should be minus L comma 0. And for D, oh guys, for D also it should be 0 minus L 0. So these are the correct coordinates. Okay, coming back to this, plus root 3 LK and RED, okay, that would be LJ cap plus root 3 LK cap. This was I. This is I cap. Okay, so we have got the 4 vectors. Now we will write the 4 force vectors. So FEA will be written as K capital Q small q. Okay, then the vector, the REA vector by REA mod cube. So this will become KQQ and then minus L, I think it was minus L I cap plus root 3 L K cap divided by. Now notice that the magnitude of this vector, the magnitude, if you write it here, REA vector magnitude, that will become L square plus root 3L square root of that. So this will become 4L square root, so it will become 2L. Okay, and all these vectors have the same magnitude. All these vectors have the same magnitude. That is actually evident from the figure itself. All these lengths are identical. Okay, so all the vectors have the same magnitude. So we will write 2L cube. Okay, likewise FEB vector. FEB vector, that would be written as KQQ, and then it will simply become minus LJ cap plus root 3L K cap upon 2L cube. Okay, FEC vector, that will become KQQ and then Li cap plus root 3L K cap divided by 2L cube. I think you are getting the point. If you are doing this question yourself, you must have got what is happening by now. Okay, this will become L J cap plus root 3L K cap by. So guys, if you notice that ultimately we have to add these 4 vectors, and when we try to add these 4 vectors, notice what happens. Okay, this part is common in all the 4 vectors. Okay, this part is common in all the 4 vectors. Okay, so minus Li cap gets cancelled by plus Li cap, minus Lj gets, so only K component remains, and that is what we were expecting. We were expecting the force, okay, we were expecting the force in this direction, so only K component is left. So we are not only getting the magnitude, we are also getting the direction. And what would be the net value that we are getting? Okay, what would be the net value? So when you add all these vectors, I encourage that you do it on your own. It becomes 4 times of KQQ root 3L divided by 2L cube, which ultimately becomes 4 root 3 KQQL upon 8L cube, which we can then write as root 3 by 2 KQQ by L square. I hope I have not committed any mistake. Yeah, so this and this is all in K direction. So okay, so we got the magnitude as well as the direction. So you see guys, this is where the vector form can be very useful to us. Now it may look very intimidating to use the vector form, but you do one question on your own and you will realize that there is quite a lot of repetition of the same step that you have done in such question. You just need to be careful enough and the calculations aren't complicated. They may look lengthy, but once you execute them, you will find that they are not that difficult. Okay, you can do them on your own. All right, guys. So today we stop here. We'll continue this chapter in our next session also. I'll see you next week. Take care, students. I hope you are enjoying this series. Again, in case if you felt that the speed was a bit more, you can slow down the video later and you can watch it. Okay, and in case, just in case if you felt that I was slow, which I'm pretty sure I wasn't, then you can speed up the video and you can watch. I'll see you next week, guys. We'll start with electric field. Take care, everyone. Bye-bye.